Let's call here support A. Let's call here support B. Now, in doing this, have support A, support B. Now, we're going to take the equation, the bending moment expression, and drawing the bending moment and shear force diagram for a simply supported beam. And we have a beam on the board we're going to use as an illustrative example. Now, we have this simply supported beam. We have a turning moment of 20 kilonewton, 15 kilonewton UDL, and a point load of 20 kilonewton and 30 kilonewton respectively. Now, the first thing we're going to do, we are going to take all the vertical forces to be zero. So we'll say that sigma Fy to be equal to 0. If sigma Fy is 0, we have, when we draw the free body diagram, horizontal force at this point, let's call it HB. So we have a reaction at this point. We can call here RA. We have a reaction at this point. We can call it RB. Okay? So these are the forces at the support of this beam. Now that sigma Fy is 0. Okay? If sigma Fy is 0, we have all the vertical forces to be equal to 0. So when we take the algebraic sum, we assume that all the forces acting downwards are negative forces, while the forces acting upwards are positive forces. All right? So by implication, RA and RB, they are acting upwards, so they assign positive values. While we have all the vertical forces, 30 kilonewton point load, 15 kilonewton per meter UDL, and a 20 kilonewton point load, all acting downwards, so they will be assigned a negative value. Okay, so based on this, we can now say if the algebraic sum of sigma Fy, which is the vertical forces, Fy to be 0, it means that we'll have the forces. First force here is RA. We have negative 30. We have, this is a UDL, 15 kilonewton per meter, so the force here will be minus 15 times 4.5. Okay, we have here to be 20. Okay, all equal to 0. To be equal to 117.5 kilonewton. All right. Now the next thing we are going to do is to get sigma Fx. Sigma Fx is 0, meaning all the horizontal forces are equal to 0. We have just one horizontal force, which is HB. So we can say that HB is equal to 0. Now the next we are going to take is summation of moment about any point. Let's say summation of moment about point B. Let it be 0. So the algebraic sum of moment about B is 0. So this is how you go. This is a force going up. This is going in a clockwise direction. We have these forces clockwise direction about B, moving towards B. Then we have 10 kilonewton load coming. This one is coming this way. This is an anti-clockwise direction, moving towards B. This load is equally moving. This load is also moving in anti-clockwise direction towards B. This one is moving in anti-clockwise direction towards B. So for this, an anti-clockwise direction towards B, while here is already an anti-clockwise moment. So you can see that all the moments here are anti-clockwise. So summation of moment about point B to be 0. let's assume all clockwise moments are positive while all anti-clockwise moments are negative. So we are going to have that RA positive, the moment become RA times the span. This is 4, 7, 7 plus 4, that is 11, 11 which is 15.5, okay? So we have 15.5. So this becomes 15.5. We have 8.5. We have this one. It becomes, now this load we act at this point. The load becomes 15 times, it becomes minus 15 times 4.5 times the center plus 4. But RA plus RB is equal to 117.5. Therefore, RB becomes 1 is to obtain the moment expression. So let's quickly do that. Let's quickly do that. Now, for the moment expression, we have, remember, we have the beam as this. This is the beam. Here is from here to here is X. Have it to X. This is a section. This is our M of X. Our moment expression. We have our F of X, which are shear force expression. So here we have 47.54 kilonewton. So quickly, the next thing we are going to do is to take moment about the point KK. So if we say summation of moment about K to be 0, we are going to have 4754 times X, which is the distance from here to here. And we have a moment here, which is M of X equal to 0. This force will not participate because it's already at point KK. So, all right. So, point KK. So, we're going to have it as 47.54x is equal to M of X. Now, our M of S is the moment expression for this particular load boundary. So, we can say that the moment at any point between 0 and 4 is 47.54x. All right? So that is a moment expression. Now, we've just gotten a single boundary in this particular beam. We'll get other boundaries. The boundary we are going to take when we look at the load on the board is going to be from 4. This is 0 to 4. Now, we're going to take from 4 to 3. Okay? From 4 to 3. And that will be, we call it, it becomes from 4 to what? To 7, because we have 4 plus 3 here to be 7. So the boundary we are taking now is from 4 to 7. So now let's quickly 4.5. And if we add it, 7 meter plus 4.5, if you look at the board, you can see it is from 7 meters to 7.7 plus 4.5. So we are taking from here to here. So from here to here is 7, and from here to here we are going to get the value. So let's get the value from here to here. This is 7 plus 4. This will give you 11.5. So from here to here is 11.5. That is where we are interested. Now the load boundary we are interested in is from this point to this point. So we are going to draw the bending moment and the shear force expression for this particular load. So let's draw it. We are going to cut a section across this load boundary, which is this point. Okay, so let's go over and let's do that. Let's cut a section across that point. We can call the section whatever name we wish. All right, so let's take a section quickly. We can now take from 7 meters to 11.5 meters. So that is a range for X. All right. So if we do that for X, we are going to draw the points let's call this point, whatever you want to call it, you can call it anything, 1, 2, or you call it section 1, 1, whichever you want to call it. Now we have our moment here. As usual, we have our shear force expression, which is a function of x. So this is what we have. The loads as this. We have an applied moment at this point, which is 20 kilonewton meters. We have a point load at this point, which is 30 kilonewton. We have a uniformly distributed load, which we've cut between, and we have from here to here, we are taking it to be x. Okay, all right, so this is what we have. Now let's go over and let's write the shear force expression. Here remains 47.54 kilonewton. So we go sigma Fy to be 0. All right. Sigma Fy is 0. So let's work it out. So let's redraw it. Have it as this. No. We are going to do quickly. We have here to be 47.54 as usual, 47.54 kilonewton. So we are going to solve this expression. Now solving this, you are going to have sigma Fy again, 0. So we'll have 47.54 minus 30, then minus 15. All right, minus 15. Now we are going to take note of this. We are interested in this boundary. This is where we are interested. So from here to here is 7 meters. So, and we have here to be x. So how do we obtain this? This becomes x minus 7. X minus what? 7. All right. So that is a point. So if that is a point, it means we are going to have here, for this load, we are having minus 30. Here becomes 15 times x minus what? 7. All right. So this would be the shear in that point, because this load times this will give us the force. So it becomes minus 7. And then we'll have our f of x, which is coming down as f of x, and everything is equal to 0. So if we do that expression, we're going to have our f of x to be equal to 47.54. All right, 47.54 minus 30, minus 15, bracket x 7. So we have our f of x becomes, let's do this and let's see what we have here. So for minus 30 from this, we're going to be having 17.5. We're going to be having 17.54. So 17.54 minus 15, x minus 7. So this becomes the expression for this shear force. Now, I haven't got to the shear force expression. Quickly, let's obtain the moment expression. All right. So quickly obtain the moment expression for this point. Now, the moment expression is also as simple as we've done before. We can say summation of moment about section 1, 1, let it be 0. So we can now say that 47.5, sorry, 47.54 times the distance from here to section 1 is x, and we have a moment here which is minus 20. Okay, we have the point load which is minus 30. All right, now minus 30 is going to be multiplied. This is going to be minus 30 times the distance to section 1 is x, becomes 30 bracket x minus what? 7. So that is what we have. Then we have this one. It becomes minus 15 bracket x minus 7. Now this load is going to act at the center here. So it means it's going to act at the center. So we'll multiply 15 kilonewton by s minus 7 becomes the load. And the distance of that load to our point of interest will becomes, this becomes times 2 over 2. Okay? All right? Then we have our moment expression, which is our m of x. And we have that to be negative. All right, so if we continue, we're going to have our moment expression m of x to become 47.5x minus 20 minus 30x. All right, minus 30x 7. All right, then we have minus 15x minus 7 all squared over 2. So this becomes our moment expression. Now what it means is that once we have this expression, we can substitute the values of x within this boundary range between 7. This is for 7. This is the boundary range, remember. This is for between x is equal to 7 and s is equal to 11.5. So when we do that, we can get the values of x in that range. So now, having got it, so having done this, the next boundary condition we are going to take is between 11.5 to 2, which will give us between 11.5 to 13.5 by adding 2 to it. So we can now say 11.5 is less than x and s is less than 13.5 meters. Okay, so that is the next boundary, load boundary we are going to take. So if we take that one, quickly we can draw this thing again. Quickly, we have it as this. Remember, here is 20 kilonewton meters. Remember that here is 4. Remember that here is 3. Remember, we have a UDL. We have a point load here of 30 kilonewton. We have this one to be 15 kilonewton per meters, and we have a point load of 20 kilonewton. And remember, from here to here is 2 meters. Here is 4.5, and here is 2 meters. So this is what we have, and we have the support at this point. So now we are going between this boundary. So this is where we are. So we are cutting a section across that boundary. All right, so if we do that, we will not see this. So this one is going, this one is going. All right, this one is going. So now we are going to have our value for x running to. So let's call here whatever I want to call it, maybe zz, whatever is the section. The moment remains the same, m of x. We have the shear f of x. So this is what we have. All right, so with this we can confidently obtain the moment expression and the shear force expression. This is the second to last zone. After this, we'll do the final one. And if we do this very well, we'll have our moment expression as this. Can have our shear force. Let's start with the shear force. F of x. We'll do that. We're going to have F of s to be 47.54. We're going to have minus 30, and we're going to have can just assume the value from that point will be constant. All right. So if we solve this amicably, we are going to discover that this is 17.5. We're going to have a constant value for shear along this path. Okay. This boundary. So that value, we have it to be 49.96 kilonewton as the value. So that value will be constant throughout that load range between 11.5 meter to 13.5 meters. So that is what we have for the shear force for this particular load zone. Now, quickly, we are going to do the moment for this particular load zone. Same thing like we did in the previous one. We're going to do the moment for this load zone. Okay, so let's for the moment. Now, like we did before, the moment we have this as a beam. Yes, 20 kilonewton meters. Yes, 4 meters. Want to get the expression for this one. Okay, this is where we are. Remember, we called it section ZZ. Need to redraw it so that we can calculate it. All right, so we have the moment expression. This is the shear force expression. Both are functions of x. These are x. All right. 3 is 11.5 to 13.5. So within 11.5 to 13.5, we're going to have a constant shear of this value. So this value of shear is not going to be in terms of x. So we're going to have it as this minus 30. Okay. Now let's obtain the moment expression for this one. We're going to have the moment expression to be this. Remember, this is 47.54x. The distance to x, moment about x. We have a turning moment of 20 kilonewton meters. We have 30 kilonewton force. It becomes 30. Now the distance from this point to our ZZ section, look at the distance here, which is to our ZZ section. So to our ZZ section. So here is 4.5. So 4.5 plus x minus 11.5. So this becomes 4.5 plus x minus 11.5. Okay, that is one of the first. Then we have the UDL. Similarly, the UDL becomes 15 times 4.5. That is the force. So this force acts at the center, which is the center of 4.5. So which is 4.5 divided by 2. So it will also span to Z section. So it becomes times 4.5 over 2 plus x minus 11.5 close bracket. So the total moment expression for this becomes equal to 47.54x minus 20 minus 30. Let's work on this. This becomes 4.5 minus 11.5. That gives us 7. So I'm going to have here to be x minus 7. All right. Similarly, for the UDL, we're going to have it as 4.5 times 15, which is giving us 67.5. So we're going to have minus 67.5 open bracket, that is the load. Now the distance becomes 4.5 over 2, which we've done before. So we'll just work on it. We'll say 4.5 over 2 minus 11.5. We do that, we're going to have 9.25. So we're saying that this becomes 67 uh, x minus 9.25. Okay, so this is the value. So the final moment expression for the, okay, so this is 9.25. So now we have gotten this. I think we need to obtain the last one. So if we have the last boundary, we can now plot the bending moment diagram. All right, so I've written the last zone. I've written the last zone. It's time for us to begin to substitute the values of x from 0 to 4, 4 to 7, 7 to 11.5, and we're going to substitute them, and 11.5 to 13.5, and 13.5 to 15.5. All right. Now let's begin to substitute them. You can begin to substitute them from the expression on the board. When x is equal to 11, we can see the values. When x is equal to 13.5, we can see the values. X is equal to 11, then we'll have the moment to be 239.835. X is equal to 13.5, we have the moment to be 139.915. X is equal to 13.5. We substitute that again. Let's substitute that. Okay. So the moment expression for the zone 13.5 to 15.5 written on the board. So let's substitute when s is equal to 13.5 into that expression. We have all right, okay. So if we do that, x is equal to 13.5. Okay, so substitute s is equal to 13.5. We'll have that when s is 13.5, our moment is 139.915 kilonewton meter. All right. So once we're able to plot these various points, we can now determine we can now plot the bending moment diagram. Now note that the bending moment diagram we are seeing on the board, if you want to draw it according to the zone, you have it like this. Remember, where the UDL is a parabolic curve, and the way the bending moment diagram is, it can't be like that because between 7 to 11.5, there should be a parabolic curve. So the shape of the curve, we are going to differentiate. We are going to differentiate the moment expression between 7 to 11.5. When we differentiate that expression equated to 0, then we'll have the value of x for the turning point of that parabolic curve. When we substitute the value of s into that same expression, we'll have that the maximum moment at that particular point is 323 kilonewton meters. That is the maximum moment of that parabolic curve. And of course, that moment automatically becomes the maximum moment of this particular beam. All right. So, similarly, the maximum shear force of this beam is 69.96 kilonewton meters. So with this, I believe we'll be able to do anything on bending moment. Thank you very much.